Hi everyone, this is Gakhar from Idaho National Lab. I'm sorry I missed the chance to be there in person and give this talk. But today I will be talking about effect of fission products on molten salt corrosion for nuclear reactor applications. So, but when in a reactor application, this salt, coolant chemistry sees a change upon nuclear fission. So, because the fission products from the structural material, they can come in the salt, and that impacts its chemistry. And then other way around also, as there is more buildup of fission products or corrosion products in the structural material, it can actually become more corrosive and it can impact the structural material even more. So understanding all this chemistry, the fundamentals of this interfacial chemistry is important to understand uh, the the application of nuclear reactors, like how which structural material might be more applicable, and what kind of longevity we can expect from these structural materials. So like as we discussed, molten salt chemistry actually has a very complex impact of corrosion, because it is impacted by any impurities in the salt, its redox potential, and any fission product buildup in the salt. So today I will talk about one particular fission product, europium chloride. It is known to accelerate corrosion of structural materials in molten salt, specifically molten LiCl KCl eutectic salt. LiCl KCl eutectic salt is used as the electrochemical media for pyroprocessing application, which is reprocessing of used nuclear fuels. So that's why I'm considering this system here to for today's talk. And also then in general, like monitoring of such corrosion reaction, it has direct implications on molten salt reactor design. So today my talk will focus on two projects that are funded by US Department of Energy Office of Science, and these two are Basic Energy Sciences program to look into fundamental aspects of salt chemistry. First is Energy Frontier Research Center, known as Molten Salt Under Extreme Environments. It's a big consortium of three national labs and 6 partnering universities, where the overall objective is to look into the fundamental and predictive understanding based on atomistic and molecular level description of molten salt, bulk and interfacial chemistry, and to look into the effects of solute, impurities, and radiation. So we work together in a collaborative approach. Like an example is shown here. To look into the speciation of metals in molten salt, we combine different approaches like X-ray absorption spectroscopy techniques and optical spectroscopy techniques, and also the combination of simulations to understand the complete picture and how this all comes together and affects the molten salt chemistry. In another program, also funded by Basic Energy Sciences, we are looking into understanding and prediction of radiation induced iodine speciation. Iodine is a high yield fission product in the molten salt reactors, and which is known to be a concern for environmental release, because its uptake in because it can be uptake into the human thyroid gland. And during 1975 molten salt reactor experiment, conducted by Oak Ridge National Lab, it was found that more than 60% of iodine generated by the reactor was not accounted for, could not be accounted for. So where did it go? So this is our program is specifically looking into that, and here's the team that's looking for that iodine. So I will start with one of the main tool I use for these projects, which is spectroscopy. So this is the setup we have at Idaho National Lab. We have a furnace that's designed to do multiple spectroscopy techniques. We have 10 optical ports, and we have a cuvette holder that can hold up to 5 cuvettes, and we were the first one to design this. And this is housed inside an inert atmosphere glove box. The reason is that these molten salts we can only handle inside the glove box, because their chemistry is impacted if they come into contact with moisture or oxygen. So this glove box sits inside the glove box, and we use fiber optic cables that connect into these ports, and we do spectroscopy. Let's say in transmission mode we do optical spectroscopy in transmission mode, in UV range and in near IR range. And we also, with using the spectrophotometer that's outside the glove box. And we also have Raman spectroscopy that we do in reflectance mode using 5th port, and we then still have space for combining other spectroscopy approaches here. We can also do electrochemistry in situ. So each of these cuvettes have a slot up on the top where we can introduce electrodes, and we apply potential, and we can change we can probe the change in the salt chemistry using spectroscopy. So design of this furnace and other techniques and furnaces and cell holders we have designed are in one of this paper. So coming to the interaction of europium chloride with structural materials. So since we are looking into the fundamental aspect, we started with pure nickel, and we are looking into pure nickel, chromium and vanadium here. So looking at the Gibbs free energy of these reactions, looks like all of the reactions of europium chloride with metals nickel, chromium and vanadium, they are all thermodynamically favorable, since the delta G value is negative. But however, not every fusion product might do that, because look at the samarium chloride. Samarium chloride's reaction with nickel is not thermodynamically favorable. So now we are trying to use some our optical spectroscopy techniques to understand this phenomena further, like what happens and how fast this happens, understand the kinetics of this process. So here I am showing the standard spectra of nickel chloride, chromium chloride and europium chloride. In the red you see the spectra for nickel and it shows up between about 400 to 800 nanometers. Chromium 2 plus shows up between 600 and to 1400 nanometers, and europium shows up in the UV range below 500 nanometers. So so this is europium peak, but we look into europium when it's saturated. So we work at, because we are trying to probe nickel here. So we start with europium chloride 1 weight percent loaded into lithium chloride potassium chloride salt, and it gives a peak like this. This is saturated peak for europium chloride in the region above 500 nanometers. It doesn't have any features. Then we drop 1 centimeter wire piece of nickel metal. It's 1 millimeter in diameter, a very small piece that just goes and sits at the bottom. So we drop a piece of wire, and then we start a cyclic spectroscopy study to see what happens if anything new species comes up in the salt. And we see that this nickel metal is very quickly oxidized by europium chloride present in the melt, and which produces nickel chloride. So nickel 2 plus gives this spectra. This is nickel 2 plus spectra, and it starts showing up as soon as 4 minutes. And so this gives us an idea on the kinetics of this reaction, how fast this reaction is. And right after about 160 minutes this reaction was saturated, like we could not see any more further growth of this peak intensity. So we stopped this reaction after 160 minutes, and from ICP analysis we found that there is about 400 ppm of nickel build up in the salt. Now, looking at this is the reaction in absence of europium chloride. When there is no europium, we don't see we don't see any peak for nickel to start with, of course, and then we drop nickel wire, and then we let this reaction go for again 160 minutes, but we don't see any buildup of nickel in the salt. So there might still be little bit reaction of oxidation, corrosion of nickel here, just because of high temperature and lithium chloride, potassium chloride base salt. But the main idea is that in the absence of europium chloride, there is not a very fast degradation of nickel metal. Now we wanted to study that what happens if we go to some other melt. So this is a sodium chloride magnesium chloride eutectic melt. In this case, also, like, we started with a melt with same like 1 weight percent europium chloride concentration, and then we let it dissolve for some time. We let it go into the matrix really well, and then we drop a nickel wire, and then we probe this reaction again, and in this case also we see the buildup of nickel 2 plus in the melt. So this reaction does proceed in this case. So europium does have similar impact, but the kinetics seem to be slower in this case compared to lithium chloride, potassium chloride eutectic. So, and now here we are changing the fission products. We are looking at samarium chloride in the salt. So we went back to LiCl KCl eutectic system, and we in this case we loaded 1 weight percent of samarium chloride instead, and then we drop a nickel wire, and in this case we did not see any buildup of nickel. So after about 96 minutes, we terminated the experiment since we were not observing any change in the spectra. And but again, we don't expect thermodynamically also any reaction between samarium chloride and nickel metal. So this is what we were expecting. So our experiments with in the LiCl KCl melt were very interesting with nickel. So we wanted to see how it might affect, let's say, a simple alloy like nickel 20 chrome. So in this case, or like what happens if there are more than one metals present. So we looked into nickel 20 chrome. In this case, now we see buildup of nickel, but a little bit less than case when we saw for nickel. And to our surprise, we did not see any chromium here, although if you see the delta G value for chromium is lower than nickel. So we were expecting to see chromium here first, or more than nickel, but we did not see any, and we let this reaction go for a longer time, for about 240 minutes, but we did not see any chromium buildup. Maybe there's presence of little bit, but it is still within the noise level, so we can't say for sure like we see chromium here. So but ICP analysis shows that there is chromium in the salt. It's actually much more than nickel, but the reason we don't see it spectroscopically is that chromium has very low molar absorptivity, which means that we need very high loading of chromium in any in the system to actually see spectroscopically. So it's there, but we are not able to see it spectroscopically. And then again, to show the reaction in absence of europium chloride, when there is no europium chloride in the melt, this is the base lithium chloride potassium chloride melt, and we drop nickel wire, and we don't see any buildup of nickel chloride in the salt. So this again proves that this is all the impact of europium chloride, even though it's just at 1 weight percent. And I would also mention that in all these reactions we are keeping the temperature constant at 500 C, because this is the temperature of the actual pyroprocessing process. It's done at 500 C. So that's what we were interested in looking at. Now we wanted to see what's happening at the interface, like how is this corrosion proceeding. So we see that there is a very large chromium depleted layer. Here you can see in yellow, this is all chromium depleted layer. There's some also salt seems to be penetrated into the nickel 20 chrome wire surface, but it seems to affect nearly entire TEM lamella, which is the blue region. So but interestingly, in this case we don't only see intergranular corrosion, but we also see intragranular corrosion. Like in addition to intergranular, we see intragranular corrosion. And also for intragranular corrosion, we see that there is a preferred crystallographic attack on one particular plane, 001 plane. So it's very interesting. It's going into a certain plane. So we are looking more into this, and all of this characterization is done by my colleague Kosto Bhavane at INL. And this is the A-star orientation mapping of the corroded nickel 20 chrome sample. In this case, we see that in the corroded sample, which was corroded in presence of europium chloride, the black region with green dots, this index salt. So it's more likely like a amorphous region, and all the individual color regions are individual grains that are shown with different orientation. And this is the structure that looks like without europium chloride. So all the grains are still intact on the surface, but in case of europium chloride, seems like this all of the grains are like this surface has impacted a lot, and this all grains are going in they're going away from the surface. So we are looking into more detail into understanding the surface of nickel wire also. And now I will move to vanadium wire. So first we looked into nickel wire, then nickel 20 chrome wire, and now we are looking into vanadium wire. And this is the spectrum from literature to give you an idea on what we are looking for. So how vanadium 2 plus looks like versus vanadium 3 plus. And this is our results. In this case, we dropped same 1 centimeter size of vanadium wire into the salt, and we saw buildup of vanadium 3 plus very soon. Like in about 20 minutes, it was a significant buildup of vanadium 3 plus in the salt melt. And with time, then we saw that vanadium moved from 3 plus state to 2 plus state, and ended up at the end of the reaction, the equilibrium state was 2 plus. So it was very interesting to see that how this shift in oxidation state happens. And like this is only possible spectroscopically, because if we just look at the salt and do some post corrosion analysis, we will only see maybe just how much vanadium is present. We can't even tell what oxidation state that is. And using a in situ technique like this, we can actually see like different oxidation states that are forming. So this gives us a little bit more insight on how the process is happening. So overall, through this study, our summary is that europium chloride impacts the corrosion of structural materials. And we looked into like nickel and vanadium metals, and also the alloys like nickel 20 chrome alloy. And vanadium specifically, it goes through a multi-step oxidation process. However, some of the fission products like samarium might not be such concern for the corrosion aspect. So now moving forward, we want to see how the iodide species might affect, like how the halides there might affect. So going from chloride to iodide, how that impact that chemistry. So we are starting with thermodynamics again. So looking into the delta G values of europium chloride versus iodide, how does that compare when we look into the oxidation of nickel, reaction of nickel? So delta G value of delta G value of reaction of europium iodide with all these metals is lower than compared to chloride counterpart. So this is for nickel. Again, for chromium also, for iodide it is lower compared to chloride, and for vanadium also, for iodide it's lower compared to chloride. So which means that this corrosion of these structural material will be very much faster, is expected to be much faster when we go from chloride melt to iodide melt. So now our next study is lithium iodide potassium iodide melt with europium chloride. So here I'm just showing like what we are looking for. In our previous study, we were looking for nickel in chloride form. So this is what we were looking for, like this is the spectrum of nickel 2 plus in chloride melt. In iodide melt, this is how nickel looks like at 500 C. So this is the feature we are looking for here, and this is our results. So this is the spectrum of europium chloride in lithium iodide potassium iodide melt. So it does not have any feature in this range above 450 C. But then when we drop wire and we monitor the reaction change in the salt chemistry, we see the buildup of nickel iodide in the melt very fast. And I would like to just highlight here again that we even visually we see a big change in the salt, and again we are not applying any potential, we are just dropping the wire and it's sitting at the bottom of the cuvette. So also interestingly, we did ICP-MS analysis, and it shows us that nickel in salt, it's 10 times more in iodide melt compared to chloride melt. So this shows again how fast is the kinetics in this reaction, and how much the change in the halide impacts this chemistry. So this is what we were looking for, that yes, fission product europium has an impact, but it has higher corrosion potential in iodide melts compared to chlorides. So with this, I would like to thank the sponsors. This work was supported by US Department of Energy Office of Science, and I would like to thank all my contributors and collaborators here who have helped in different parts of this story. And here's my contact information. If you have any questions or comments, please feel free to reach out. Thank you so much for your time.